Hey, so this is Joe, and this is the third video of the 11th chapter of Stewart's Calculus, and we're going to be talking about comparison tests for finding the convergence or divergence of infinite series. So, we got two kinds of comparison tests. We've got kind of the just straight ahead, straight down the line comparison test, where you just compare the convergence and divergence of two series, and then you've got the limit comparison test. So first, we're going to talk about the straight comparison test, and that's kind of my own name right there. But so it says that if we've got some series b of n that we know converges, and so that could be a p series, some easy ones would be like a p series or a geometric series, and we have some other series a sub n that's always less than or equal to the known series b sub n, then that unknown series also converges. And then we kind of have the corollary where if we have some series b sub n that we know diverges, think like a harmonic series, we know that, then if we have another series a sub n that's always greater than or equal to b sub n, then that new series diverges. And so we can kind of illustrate this with a graph. So you know the p series 1 over n squared, we know that that converges. And we also know that the p series 1 over n cubed also converges. And that kind of works based on this comparison, because 1 over n cubed is always less than or equal to 1 over n squared. So it's always smaller than a series that already converges, so that means that it's got to converge as well. And that we kind of have a similar concept with convergent improper integrals. If we've got a smaller area than an already definite area, then that smaller area has got to be definite as well. And you can kind of think about those in similar terms. And same with the divergent series. If we've got the harmonic series 1 over n, if we've got another series that's say 2 over n, right there, that series is always going to be greater than an already divergent series that doesn't go to a single number. That means the one that's always greater isn't going to go to a single number as well. And we can think of this also in terms of improper integrals. If we've got an indefinite area and then we've got a greater area than that already indefinite area, then that greater area is going to be indefinite as well. So that's how you can think of this sort of straight comparison test. And then the limit comparison test says if you've got one series b sub n and another series a sub n, then if we take the limit as n approaches infinity of a sub n over b sub n, and we get some real number that's greater than 0, then both a sub n or b sub n will either both converge or both diverge. And so this is a comparison test, because the strategy you have to take is, well, so I'm going to get one series that I know the convergence or divergence of. So say you use a harmonic series, you know it's divergent, or use a p series, or use a geometric series as b sub n, or it could be a sub n, however you like, and then an unknown series, which is the other one, and you divide them. If you get a constant, then you know that the unknown series will have the same divergence or convergence as the known series. So that's why it counts as a comparison test. So those are the two comparison tests. They're not too complicated, I don't think, but if you're having a little bit of difficulty with them, just conceptualizing them, we're going to do a couple problems that'll use them both. So here we go. Alright, so we're going to do number 4 on page 750 of your book, and it asks us to figure out whether or not the series n cubed over n to the 4th minus 1 is convergent or divergent using one of the comparison tests. So, we see in this function, and so, yeah, the question of the day is going to be, which comparison test do we use? Well, the straight-ahead comparison test is easiest to use when we have a function that we kind of feel like looks like one of the three functions we know converges or diverges. So like harmonic, p, and then geometric series. So this one, we've got something to a power that's greater than 1 in the denominator, so we kind of might feel like, oh, that looks sort of similar to a p series. So let's try to compare it to a p series. Let's try to compare it to the largest of the p series, because that's going to be easiest to prove that this is smaller than that. And we only want to try to prove that this series is smaller than a p-series because the p-series is convergent, and if we show that it's greater than a p-series, then a convergent series, we haven't really shown anything useful in terms of proving the series is convergence or its divergence. So we're going to compare it to the p-series 1 over n cubed, and we know that that's convergent. So let's start doing some algebra. So we will then get n to the 5th over n to the 4th minus 1 is less than 1. We don't really have any intuitions about that. Then we have n to the 5th is less than n to the 4th minus 1. And now let's try subtracting this n to the 4th over, and we'll factor, and so we'll get n to the 4th times n minus 1 is less than negative 1. And then let's divide this over, and we'll get n minus 1 is less than negative 1 over n to the 4th. And then we can add this one, and what we'll get is n is less than 1 minus 1 over n to the 4th. And now this seems false. So remember, we're starting at n equals 1. So if we plug in 1 for n, we'd get 1 is less than 1 minus 1 over 1, which is 0. We would get 1 is less than 0, which is false. So this inequality is false, and so does this. So our comparison test for that failed. So that means that this series is actually greater than this p-series. And this p-series, remember, is kind of one of the smallest ones. So maybe our intuitions were wrong. Maybe this series is actually divergent, in which case, let's try comparing it to our harmonic series, which we know is divergent, 1 over n. And so we'd need to prove that this series is greater than 1 over n if we're going to prove anything. Because, remember, based on our comparison test, we can only prove it's divergent if we show that it's greater than a divergent series. So let's try doing the same deal. We'll get to get to a place where we can show clearly that this series is greater than that series, then this inequality holds. So we get n to the 4th is greater than n to the 4th minus 1. Already, we have a very strong intuition that this is correct. We put any number in here, it's going to be greater than the same number minus something. You know, we put in 1 for n, we'll get 1 is greater than 0. Yes, we put a 2 in, 2 to the 4th is greater than 2 to the 4th minus 1. This is definitely correct. That means this is correct. And so since we've clearly shown that this inequality holds, we can say that the series is in fact divergent by comparison to a harmonic series. And now this statement is very important on the AP to show that you know what you were doing and what kind of series you were comparing it to and what kind of test you were running. So that's kind of an example of how you should go about using the straight ahead comparison test. Now let's go do another problem that'll involve using the limit test. Alright, so we're going to do number 22 in your book on the same page, and it asks us to figure out whether this series diverges or converges. So this doesn't really look like either a p-series, a geometric series, or a harmonic series very much. So I don't think a straight ahead comparison test is going to be very useful here. However, I kind of have an intuition based on the fact that the denominator is to the 3rd degree and the numerator is to the 1st, that the denominator is going to get a lot when n starts getting towards infinity. This denominator is going to get big a lot faster than the numerator, and so this will probably end up being 0. It'll converge to something. That's kind of what my intuition is. So let's try to compare it to a convergent series. So make our a of n the convergent series, and we're going to make that. So a of n, let's call that this series, 1 over n squares, that p series, and we know that that is convergent, right? And so this is going to be our b of n. So using our the limit comparison test, we get the limit as n approaches infinity of a of n over, or actually, we're going to flip it around. We're going to get b of n over a of n. It doesn't really matter which order you put it in. And so that will give us n plus 2 over n plus 1 to the third. And then we will have under this 1 over n squared, but we can really just flip that n squared up into the numerator here. So we've got this. Now let's just kind of simplify. Oh, and we have to have our limit talk. And so let's try to simplify this a little bit. We'll get the limit as n approaches infinity. Let's distribute that n squared. Then we'll get an n to the third plus 2n squared, and then we'll get an n plus 1 to the third. And when we put infinity in here, we will get our indeterminate form, so that means we can use L'Hopital's rule. So we'll get the limit as n approaches infinity of, and then we'll take the derivative up here, 3n squared plus 4n. And then take the derivative down here, we'll get 3n plus 1 squared, and the derivative of the inside is 1, so we can leave it as is. And when we plug in infinity, we'll still get an indeterminate form, so we're going to use L'Hopital's rule once more. Well, that's a 6n plus 4, and this is going to be a 6n plus 1. And so we get 2. And so we still get an infinity when we plug in for n, so we're going to use infinity over infinity, our indeterminate form. So we're going to use L'Hopital's rule another time, and I think this is going to be the last time. We take the derivative of the top, that's going to be a 6, derivative of the bottom, that's also a 6, and so this limit is equal to 1, and 1 is greater than 0, therefore this series up here is convergent by comparison to p-series. And so also this little statement here on AP free responses is very important because it shows that we know what we were comparing it to. We know that we were comparing it to a convergent series. And based on our limit test, this series must be convergent because the limit is 1 and it's greater than 0. So those are the two comparison tests. I hope that helped a little bit. And stay tuned for the rest of this chapter and the rest of Calc BC. We're going to be getting into more kinds of series and more tests for convergence and divergence. So thanks for watching.